Right, we'll get started. So hi everyone. Welcome. This will be the last in-person review I do this semester. Next week, since it's a reading day, I will still hold a review session as like a final exam review section. But I'll just do it on Zoom so that you don't have to come to campus or anything if you're not already going to be here. And then that'll be Wednesday, and then I'll hold a final review session. Monday before your exam. So Monday the 5th, I'll hold a review. Probably that like later time slot so you can do any last minute questions before your exam on Tuesday. But that's in a couple weeks. So you just have a quiz 6 on Monday, and that's like the big guy. And then classes are done. Let me see. I had a question about the final. I think it's going to be about 50% of the new material, and then I would say 25% of the old stuff. It might turn into 40% of the new material and then 30% of the old stuff each. But it'll be more on the new stuff rather than the old stuff. I guess. So that's that breakdown. I do think Dr. Bengali will give an mock exam. So that should help you out. And then once I know what his mock exam looks like, then I will make some additional practice problems just in case you need some additional questions to review before the final as well. So you'll have plenty of practice, and hopefully there's enough time for you to get started on studying with all your other finals that you might have going on. All right, are there any questions for me based off of like what's coming up in the future? Cool. All right, questions on content that we would like to see today? You want to talk about what we did in class today? Yeah. I know we kind of went through that kind of quickly. All right, so how are we feeling on reaction mechanisms? Do we want to start there? Yeah, okay. So when we look at a reaction mechanism, right, this is going to be the steps of a reaction. Right, so when you look at something that says A plus B goes to C plus D, right, it might just do A and B reacting in order to make C and D. However, that might not be all of the steps that happen, right? It might have to go through a couple other steps in the process, right? So maybe A goes to E first, and then B comes in and goes to, and that works with E to form F, and then, or I guess to form C plus D, we'll call it that. Right, so then when you added step 1 and step 2, then overall you would get A plus B goes to C plus D. Right, so the reaction mechanism is the actual steps it takes to produce those products. In a reaction mechanism, what do we call E? What is that? Yep, intermediate. So E is an intermediate. Right, it is first produced. And then consumed. Okay. What is like the other component that we talked about with intermediates? It's not pictured here. We talked about it towards the end of class today, or the end of the chapter. A catalyst, yep. So, right, a catalyst will first be consumed and then produced. Right, so that would usually appear in the first step and then in the last step. It would appear as a reactant and then it would appear as a product. When we talk about rate laws, catalysts can appear. Intermediates cannot. Okay, you cannot have an intermediate in a rate law, but you can have a catalyst.
Do you mean rate law? That's like the K with like the.
Yep, so your rate law is your rate is equal to K times A to the M power. Right, that's your rate law. So in this, catalysts are good. Intermediates are bad.
So if it said to like take a rate law, like step 2 there,
Mhm.
couldn't include E.
You couldn't include E. Nope.
Okay.
So that's kind of something that we skipped over today when we were talking about equilibrium. So I can show you what that would look like. Any questions so far on like intermediate catalysts? So if we were to take step 1 and step 2. Yep.
So I don't know if we went over this before. Our steps, will we be given steps or are we gonna be expected to figure out?
You would be given the steps. Yep. Yeah, you're not expected to like break it down. All right, so if we're given step 1 and step 2, if I told you this was a fast step and this was a slow step, which one is the rate determining step? The slow step is.
Is that the game goes wrong, like which one's fast and slow?
Yes, yep, it'll say like fast and slow next to it. Like in your slides, it gives you examples and it says slow and fast next to it. That would be given to you like on your exam the same way. Okay. So if we have a fast first step and then a slow second step, usually that means that your first step will be in equilibrium, right? And we talked about equilibrium at the end of class today, which means that the forward direction is happening at the same time that the reverse reaction is happening as well. It might look like the reaction is not happening because concentrations are no longer changing. However, it is happening. It's just going back and forth at the same rate. Okay, so if our slow step is the second step and it's the rate determining step, what step 1 or step 2 are we going to write the rate law for? 2, right? So what would that rate law look like if we were just to write the rate law for step 2? We would say that rate is equal to.
Is it the product of the reaction?
Nope, that's for chemical equilibrium. This is rate law, like the one in purple above.
There would just be like K parentheses E close with E.
Yep, perfect. Right, so that's what we would expect the rate law for step 2 to look like, given the fact that it is a slow step if our reaction. Yep.
Why is
It is an intermediate. So I'm showing you how you would get rid of it.
Oh.
Yeah, we talked to yeah, you're good. The one we skipped over today was right before the catalysis slides started. He skipped that because we hadn't talked about equilibrium, so I'm just showing you how you would do it now. So, right, this would be the rate law that you would expect. However, we said that E was an intermediate, so we can't have this here. So we have to look at the steps beforehand in order to get rid of that E that we're looking for. With step 1 being an equilibrium, we could still write rate laws for that reaction. If we were to write the rate law for the forward reaction, what would the rate law for that look like for step 1? Rate is equal to K times A, right? It's the only reactant we have. So that's going to be the forward. If the forward is happening at equilibrium, the reverse is also happening. So the rate for the reverse reaction is K times E. What can we say about the red rate law and the purple rate law if it's at equilibrium? The rates are the same, right? It's happening in the forward and the reverse reaction at the same time. The rates of the reactions are equal. So we can say that K times A is equal to K times E. We're trying to get rid of the brackets in E in our blue rate law. So what can we do to KA is equal to KE in order to help us out? Right, if we considered E a variable that we were trying to replace, what could we do?
Replace E with the.
Yeah, right, we can solve for E in our purple and red equation, right? We can say that the concentration of E is equal to K times A divided by K. We can then take that whole thing and plug that into the E that we don't want. Now we would say that rate is equal to K times B times K times A all over K. I tried to write this in different colors because the K's of all of these are not the same. They would all be different K values. Okay, so then since all of your K rate constants are a constant, you could multiply the blue K times the red K times the purple K. And that would give you like, I don't know, I'll make it a green K. K times blue times A. And that would be equal to your rate. Right, so we combined all of the K's into one giant rate constant, green K, multiplying by B and multiplying by A. And this would be the rate law for the slow step.
So each K is a different variable, like not just gonna cancel.
They're not just going to cancel it. Nope, it's like K1 times K2 divided by K3.
So that's how we always need to do it.
That would be,
It's an indeterminate, it cancels out then we need to start kind of manipulating other questions.
Correct.
Others reactions to get it.
yep. So, right, if your slow step is second, you need to look at the reactions above to say, okay, how can I use my above reaction in order to plug this into my intermediate
So
that I
if the
have?
slow step, what changes then if the slow step is first?
The slow steps first, you can just write it directly as, right, if your slow step was first,
Oh, if it was first, it would be a catalyst.
it's just it's just a catalyst or it's just a reactant and you can use it directly,
Okay.
right? So if this reaction was actually, this was slow and this was fast, then now your rate law is just rate is equal to K times A.
Okay.
Right, we only care about the slow step, we only care about the reactant of the slow step. Does that make sense?
But it doesn't matter, like, if slow first and fast is second, or does. Like, not in this particular one, but if like you had step one, step two switch, like, if it was B plus E reacting. to,
Yep.
Like the C plus D at the top, and that was your slow, and the other one was your fast. You would still have to manipulate the question, like,
So if this was instead. Right, just say it was that instead, and this was slow, this was fast, then your original rate law of rate is equal to K times B times E, you can stop there.
why can you, don't they still cancel out though?
So in this case, E is now what?
Oh, it's been reacted and then produced.
And then
that's
produce,
catalyst.
and that's a catalyst, and can catalysts appear in your rate law?
Okay, okay, thank you.
Yep. Do we all see the difference between our three scenarios? Those are really good questions. Right, so most straightforward is when step one is slow, you can just take that slow step and use it directly to write your rate law. In the case of the third scenario, right, E is now a catalyst. So now we can include that in our overall rate law. In the second scenario, it's just A we care about, so that's good there. But in our first one that we talked about, E was an intermediate, and we can't have intermediates, so we needed to manipulate using our first fast step of our mechanism. So for a catalyst, it is first consumed and then produced, so it speeds up the reaction. For an intermediate, it's something that it has to get to, so it's produced and then consumed. So it's like a hump in your overall rate of reaction that it has to get to, so it's like a energy barrier for an intermediate, where a catalyst provides an alternate route.
You said catalyst was produced and consumed.
Catalyst is consumed, then produced. Yep. Intermediate is produced, then consumed. So if you look at slide 24 from today, I believe, that one has a fast first step and a slow second step. So you can go back and practice that question. Okay, any other questions on rate laws and writing rate laws from a fast and slow step? Does that make more sense? Okay. So going along the lines of catalysis and catalysts in general, we can have a rate of a reaction. And these would be your reactants. And these would be your products. So between your reactants and your products, what's happening to our energy? Are we gaining or releasing energy? We're releasing, so is this an endo or exothermic reaction? This is an overall exothermic reaction. And what do we call this portion here? Good, this is your activation energy. All right, so at an activation energy, all right, this is an energy barrier that we have to get over. It comes to a transition state, and the peak of that, and then it falls to your products. Okay, so that is one pathway that can be taken by a reaction, right? And that would just be one straightforward thing. If we were right, if we were to add a catalyst provides an alternate pathway. They speed up the reaction because instead of going from that large purple activation energy we had in the example above, it now produces, say, maybe this one, right? This red pathway. So now your activation energy here, right, is much smaller than it was for the purple activation energy in the reaction above. So we say that catalysts speed up reactions because it's not having to overcome this large energy barrier anymore. It just has a small one that has to get over. So we don't need as much energy of our system in order to proceed to products. We only have that little bit, so it is faster and easier turnover for our reactants to get to products.
Can catalysts ever like, I guess, slow it down? Like, could catalysts ever be bigger than,
I don't think so.
okay,
I think
so we don't have-
yeah, I think a catalyst only ever speeds up a reaction. Because if it made the reaction slower, then I don't think you would use it.
Can a catalyst ever affect the energy of the reactants or products?
No, nope. So a catalyst does not raise the reaction or reactant energy, right? It wouldn't say go like this. I'll do it in purple, right? It wouldn't bring your reactants to this energy and then follow the same pathway like this, right? It's not going to do that. This is no, right? It doesn't raise the energy of the reactants. It just changes the pathway it can take at the same energy.
Another question, I don't know if it affects, if it is relating to the graphs, but earlier you said catalysts are, you said they were consumed and then produced?
Yep.
How does that, like, how does it produce the catalyst? Like, I don't know if you can explain that using the graph, but
Yep.
I already get that.
So for a reactant or for a catalyst, right, your reactants would use the catalyst to take this pathway, right, to take the red
So
pathway.
combine-
So they're combining with it, right? So at that peak, we call that a transition state. So, right, if I want to go, from arms down to arms up, I have to pass through the T position, right? So to get from arms down to arms up, right, I pass through here. This is my transition state. That's the peak that we get to. A catalyst would then, instead of me going all the way around, a catalyst would say, okay, just go straight up, right? Now I've taken that transition state. Now my arms are bent. So in my transition state, I don't look like this anymore. I look like this. My catalyst is in me. I'm like in a different state, and then that can get me to all the way up. Does that make sense?
And I guess at the end of the reaction, the catalyst is just broken off. That's why
Yep,
produced.
it's broken off. Usually it's like complex, right? Think of like it gives it a hug and then it releases the hug.
Okay.
So it's released back into solution most of the time so it can turn over and then another reactant can use it again. Yep. Yes.
In a reaction like with the catalyst there, the catalyst has an activation energy? Does
Yes.
that override the other activation energy?
Correct. Yep.
Okay,
Because no, go ahead, keep going.
well, so yeah, I was just making sure it's like, so that's gonna become the new reaction activation energy.
Yes.
That catalyst, that small one.
Yes.
Right.
Yep. Right. So think if you wanted, right, to go down a slide, you could walk up all the way to the top, right? If you're trying to win a race, you could walk all the way to the top and then slide down. Or you can do the other ladder that only gets you up a little bit and then you could slide down and you're going to win,
Okay.
right? So that's what this is doing here. It's taking this shorter path because it requires less energy in order to get to the same reaction, right? Or if reactants was the start of the semester and products was the end of the semester with an A, And you could take the blue one and you had to put a lot of effort in to get an A, or you could take the red one to get a little effort in to get an A. Probably gonna take both a little effort, right? So the catalyst just provides an alternate route in order to do that. The only way that you could increase the reactant's energy, right? Catalyst is the red line. The purple line is if we increase the temperature of our reactant, right? So the only way to increase the energy of your reactants is by increasing temperature, but catalysts don't do that. They provide an alternate pathway. We could also have a catalyst. I'll draw it in green. Right, we could also have a catalyst alternate pathway that might have more steps, right, like this, but it still ends up at the product side. Right, this would produce an intermediate here. But that reaction mechanism is still faster and still a catalyst reaction mechanism because it is not as high of an activation energy as the original one.
So then if we have the, like, those two pumps there, right, which one is our activation energy, our catalyst?
It would be the slow step one, which is the higher one. Yep.
So do we just ignore the smaller one?
You don't ignore it, but if they're asking for is step 1 or step 2 the slow step, the one that is the higher activation energy is the slow step. Yep. So in this case, the slow step is first. Right, so higher activation energy, EA, is equal to slow step. Any other questions on catalysts and stuff like that? Okay, and then,
Right.
yep,
I know a question. So you said we could change the energy of the reactants by increasing heat.
Mhm.
How would that affect the activation energy, if at all?
yep. So if we look at right, we have the one in blue, we have the activation energy in purple. If we were to raise our temperature, we now have reactants starting here, and then it follows the same pathway down to the products, okay? So what is our activation energy now? Now it's starting at the red line, so now your activation energy is only this much. So what did that do to our activation energy?
Small.
It's smaller. So is it easier or harder to get to easier, right?
So does that mean that we have an inverse relationship between the energy of our reactants and our activation energy? So as this increases, will this always decrease?
Yes,
And vice versa?
and vice versa. Yep. So, and that also plays into what's that equation? That plays into this equation. Your Arrhenius equation, or your combined Arrhenius equation. When you look at this one, K1 and K2 is related to T1 and T2 on your other side of the equal sign. Right, K1 and K2 are both rate constants. Your larger K will always be the one at the higher temperature. And that is because, right, a rate constant tells you how fast a rate is going. The higher the temperature, the faster the reaction. So whatever one is T is the higher temperature will always have the higher K value.
And then you said higher temperature equals like a lower, energy, activation energy?
Correct. Yep.
Just like what we're gonna be given on the exam, like as far as formulas go?
Yes.
Ahead of time?
Yeah, he should give you a mock exam, and the mock exam will have a formula sheet that'll be the same as your final exam as well. Yep.
Is the mock exam gonna be just new content or is it gonna be like a final?
It'll be like an actual final.
The other question might be off topic, we're talking about, like what we're doing for our exam.
Mhm.
Earlier, like when we were talking about like that, the zero rate, the first rate and the second rate laws, will we be given those equations for the constant?
I believe so. I believe you're given all of the integrated rate laws and all of the half-life
But I
formulas.
remember, at least in lecture, like we kind of broke down the equation into like a smaller equation.
Mhm.
I'm assuming we get the base equation, correct?
You would get, so for like zero order, or I guess for first order, that's the one I know the best. Right, for first order, you'll get that the ln of AT is equal to negative KT plus the ln of A. Right, you'll get that integrated rate law, and then you'll get the T1/2 is equal to the ln of 2 over K.
And that's the half-life.
And that's the half-life, yep.
Actually,
I think you're also given zeroth in second order, if I remember correctly from last semester. But I do believe you're given at least the first. And if you recognize the first, then I do believe it's given to you as like 0 for second. So if you know the first, then you just know which way the other two go. Alrighty, yep. That's a great question. So for zero order, right, we are looking at something that is just rate is equal to K, right? We don't have any reactant involved, it's just the rate constant. If rate is going to give you molarity over second, what do the units of K have to be? Anyone can answer. It has to be molarity over second, right? Your units of K also have to be molarity over second because there's nothing else to balance out that side of the equation, right? If we're given first order, we have rate is equal to K times A. A is in concentration units, so it's in molarity. So that's right, this is going to be molarity over second. And this is in molarity. We already have one piece of the puzzle. So what K has to be is the 1 over second component because we need to end up as molarity over seconds. So we need to take molarity, multiply it by 1 over seconds to get molarity over seconds. Okay, does that make sense? And then for second order, right, let's finish it off. Rate is equal to K times A squared. We need molarity over seconds. We have molarity squared. So in order to get to just one molarity on top, we need K to be 1 over molarity times second.
I guess now that we're talking about the intermediate rate laws, I remember those graphs we have that compare the emissions between each of them, but how can you tell the difference when you're just given numbers? Like just like concentration and your rates, how can you tell which if it's a first, second, or zero order?
As in like
if there's a question that I gave you the difference between like a chart with like a bunch of concentrations, a bunch of times, and then like which ones, like is it a first, second, like is there a way to tell? That's like I remember there being a homework question.
it would probably just be something that you would have to graph in that case. Not what I was gonna do. That would be, I don't think you would see that on your exam because that would take graphing calculator or Excel.
All right.
If that is something that you have to see on your homework again or something like that, plug it into Excel and then do time times the concentration or versus concentration, or do ln of concentration over time, and you're looking for the straight line plot.
Well, we forgot
Oh.
to write the same.
Nope, you're good. Yeah.
Like, you have to plug it in the calculator to be able to figure it out. Like, if it's straight line, it's not like another way.
For that type of problem, if you're looking at like times and then various concentrations, I would say it would be a graphing calculator or like an Excel situation. So I wouldn't expect to see that on an exam. That's more of like a lab assignment than an exam assignment. Exams would be more like utilizing the integrated rate law once you know what order it is, or doing the one where it has various trials and you're looking at how concentration changes and then how the rate changes. Any other questions on rates?
No, not
Oh,
really.
okay. Any questions in general? Do you have a question?
They were just about.
Go ahead.
Like, so if you have your reaction, right, are you able to just look at it and know like what order each thing?
That's a great
Yeah,
question.
because like, there's sometimes that like you're able to like,
Mhm.
like it just asks you to be able to like know that or something, but and other times you just can't, so like.
Yep. So great question. Let's go back to our original problem. So when we look at the original reaction, A plus B goes to C plus D. If you're just given the overall reaction and you're not given the rate law, the coefficients don't tell you the order. It might work out where that the coefficients do match what order it is, but it's not guaranteed. So you can't directly use the coefficients in your overall reaction for your rate law. However, if you're given the steps in your individual mechanistic steps, then here is when coefficients tell you order. Okay, so once you're in those broken down steps, that's when it tells you what the order is.
What's the way to find the order like in the overall reaction?
Yep, so if you're just given, right, A plus B goes to C plus D, in order to find that, then it brings you down to where it's like the trial 1, 2, 3, and then you're given concentrations of A, concentrations of B, and rates. And you're like 1.1.
Yes, I completely.
Yep.
You have to have that same.
Yes.
To be able to do that part. Okay.
Yep.
And that's how you find your coefficients as well, like, I think you can do that.
This tells you if you're doing this type of problem with the trials and the rates, this tells you the order of the reaction. So this will give you that's all it will give you there. Right, and in this case, you're just looking for trials where only one concentration is changing. Which I only gave you, but in case you don't see that. Other questions? Do you feel better about reaction rates? Do you want to talk a little bit about chemical equilibrium? Before we wrap up. All right, so when we look at chemical equilibrium, right, this is saying that A goes to B. And again, right, the forward reaction is equal to the reverse reaction. So A and B are happening at the same time, but the rates of the reaction are the same. So their concentrations are no longer changing, but the rate is, or the reaction is still happening. So if we look at a graph, we saw this a couple of times, right? Where you see this, right? About here, our concentrations are no longer changing. So everything past this dotted line is equilibrium. Right? The reaction is still proceeding. It's not like it just stops, but the concentrations are no longer changing. We represent equilibrium with capital K, so big K. And we sometimes call it Kc because it is the equilibrium of concentrations, right? C, concentrations.
I don't know where the equilibrium is taking place, so, the point when you say-
It's the point where the concentrations no longer change, right? So this is not equilibrium where they intersect. It's this portion here where the lines are now steady.
So is the constant for both A and B the same? Like the K value the same, or am I not understanding, like for, you have a concentration of two different substances, is the constant the same?
So, right, if we said this would be B, this
Yeah.
would be A.
No, like,
So this would be, we'll say 5, and this is 1. Right, so you have a concentration of 5 molarity for B and a concentration of 1 molarity for
Yes.
A. So how do we set up K? Is it products over reactants or reactants over products? Products over reactants. So K for this one, Kc is going to be 5 over 1. So K is equal to 5. Okay, does that answer your question?
I guess so, they don't have. So do they have like their own individual constants? I know how normally you write a rate, you write like K, A or B, like, and the time to power or something.
Yep, so the rate in K times A to the power and B to the power is different from equilibrium.
Okay.
Rate is telling you how fast the reaction is happening, right? So how fast does it reach equilibrium? Equilibrium is saying, once the reaction has done changing, are we product favored or are we reactant favored? Okay, so when we look at this, right, we said that Kc is in concentration. So whatever you plug into K always has to be a concentration. We'll talk about Kp and we'll talk about a couple other different types of K. Right, there's Ka for acid equilibrium, there's Kb for base equilibrium, there's Ksp for insoluble salts, right? There's a whole bunch of different equilibriums that you can talk about that have different notations, but it is always products over reactants. If you have something where you have A plus B goes to 2C, can we use our coefficients for our equilibrium? For our overall reaction? We can't. Yep, so at equilibrium, so once at equilibrium, for big K, we can use coefficients.
So before the equilibrium, you keep-
Before equilibrium, you can.
You can?
We'll talk about Q and stuff on Friday. But when you talk about rates, like when you talk about rates, how fast reaction is happening, no coefficients. When you talk about equilibrium, coefficients.
The rates, no go.
Rates, no go, equilibrium, you can. Rates with mechanism steps, coefficients are good.
And we're using the coefficients for what again?
For K, oh, what just happened here? Right, if we're using it for K, so K will be, we said products over reactants. So that's gonna be your concentration of C. Where do we put the 2? Is it a coefficient in front of the concentration, or is it a power? It's a power, right? So we're gonna do C squared over A times B.
Okay, so for equilibrium, we can use it for a word.
Yes.
Okay.
And it doesn't become, the exponent here is no longer the order of the reaction, it's just an exponent.
Okay.
So rates, exponents equal order. K exponents equal nothing, I guess.
So for rates, like the two's just out there, like you don't use it for anything, it's just there for like show base.
For equilibrium here, yes, yep, it's just because they're saying at equilibrium, we have, right, 2 times the number of moles of A than we do B. So that's like where that comes into play. The math, I don't, is something that I don't have a pay grade for. So it's-
You're good.
So if you were to reverse this reaction, where this 2C gives you A plus B,
Mhm.
will your constant be the same?
No, nope. So K is always products over reactants. If we switch this to 2C goes to A times B, what is the K for, oops, what is the K for this reaction now? K will equal, what's our product? A and B. What's our reactant? C squared. What is the difference between purple K and red K? But what is the, what is the relationship?
Like first,
It's the inverse, right? So purple K is equal to red K to the -1. Right? We're just taking the inverse of this one. So if if purple K is a very big number, what is red K gonna be?
first,
A very small number, right? Because we're taking the inverse of it. If purple K is a very big number, does that mean we have more reactants or more products? Big K, a very large K value. Right, say K is 1,000,000. Does that mean we have more products or more reactants?
which you will react.
We would have more products, right? If we have a very big K, that means that our denominator is heavy, or our numerator is heavy, right? We have a very large number at the top of our fraction, pulling us to a very big number. If we have a very small number, that means that we have a very large denominator. If we have a very large denominator, that makes our number small, right? If you think of 1/2, that's 0.5, but 1/3, we increased our denominator is 0.33, so we're decreasing that number. Okay, so if you have a big K, I guess it is big K. If we have large numerical K, we have a product favored reactant or reaction.
Follow-up question. What's like the bounds for that? Like, how do I know if, this may sound silly, but how do I know if my number is large?
Yep, so we say, right, anywhere from 100 or 0.01 to 100, so a magnitude of 100 in either direction.
0.01 to 100.
Yep.
Yes, sir.
So 0.01 to K to 100, right? Anything above 100, not really anything above like 400, this would be product favored. This would be reactant favored. In between, this is equal amounts. Right, you have both product and reactant at equilibrium. You will know if something is going to be product or reactant favored. Right, usually Ks are like 1.8 times 10 to the 6th, right? Something like that, or 1.8 times 10 to the -6. So
So in that same equilibrium equation there, if we're finding like break law, we
Mhm.
could not use.
correct.
The coefficients.
Right.
over there. Okay.
Yep, right. If I gave you this guy here, 2C goes to A plus B, you could not say that the rate is equal to K times C squared. Right, you
Okay.
couldn't say that.
It's only when you're finding K. like,
Yes.
Directly K. Okay.
Directly K, right? And K for equilibrium is capital K.
Okay.
K for reactants is lowercase k,
Okay. All right.
which is easy to see on an exam, right? It'll make sure it's lowercase k or capital K. Unfortunately, chemistry is not great with their uses of letters. Big T and little t would have been a lot better. Okay, questions there? And then, so I guess just to hone in on the fact, right? If we said that our first reaction, A plus B goes to 2C, was a large K, right? We said that purple K was big. It was product favored. We see that when we reverse the reaction to make it 2C our reactant, we get a net small K. This means that it is reactant favored. In both situations, C is the favorable portion of the reactant or of the reaction, right? It's favored when it's the product or it's favored when it's the reactant. It shows the same thing, just depending how you're looking at it. I think it'll make sense with some practice problems. And we'll talk about that a bit more on Friday. Any other questions on equilibrium?
You were like week halfway.
Half-life problem? Is there a specific order? First order, yeah,
The equation changes based on order
correct.
for half-life.
Yes, yep,
Will that be good for us?
I believe so.
For you?
I think so.
Like all the equations.
I mean, you're given a lot.
Like all the stuff we're given on is like the power imagery. You know, what we give them that.
You should be able,
Well, then
you
give us
should
the equations together. I can't imagine.
Yeah.
Like every equation.
Yeah. Yeah. Yeah, you get a lot. You have a very large formula sheet for your final. Alrighty.
Are we gonna get it?
The important ones, so you'll probably just be reminded that like 1 gram is 1,000 kilograms,
Yeah.
or 1,000 grams is 1 kilogram. Yeah, you've been given, you get a lot. It is. Alrighty. So for this question, you have a first order reaction has a half-life of 6.36 days. How long in minutes will it take for a sample at 0.1000 molar to reach 35% of its original value? Do you want me to walk through it? Yeah. Yep. So this kind of combines everything that a half-life formula could ask you, or a half-life type question could ask you. So when we know that we have a first order reaction, what we want to look for or remember is that T1/2 is equal to ln2 over K. It might be given to you as 0.693. It's the same value. And then we want to remember that the integrated rate law for a first order reaction is that the ln of the concentration at time t is equal to the negative KT plus the ln of the original value. So from this question in the beginning, we say that a first order reaction has a half-life at 6.36 days. Using the half-life, that is 6.36 days. This is T1/2. If we know T1/2, we can solve for K, right? Because the rest of the question is asking you how long in minutes will it take for a sample at 0.1 molar to reach 35% of its original value. So we need to know this T value. We're given 0.1, which is A0, and we're given 35%, so it would be, we know AT, but we don't know K and we don't know T. So we can utilize the half-life formula and the half-life that we have to solve for K here. So we can take 6.36 days, and we'll get ln of 2 over K. And then if we solve that, then the ln of 2 is K is equal to 0.1091 over days. If you wanted to, you could put days into minutes first, or you can do it at the very end. It doesn't really matter. Okay, we now know K. We can use K in our integrated rate law now. We're given an original value of 0.1 molar, and then we want to reach 35% of its original value. So what is the A at time t going to be? 0.035, so we'll take ln of 0.035, because that's 35% remaining. We'll plug in negative K, which is negative 0.109 day, 1 over days.
Where are you getting that?
Because we start with 0.1.
Oh.
Yeah. It'll, if you plugged in 1 and 0.35, it would be the same.
Can we put 35? Are we able to put 35% in there? Would that still work out at the end? If you put like ln 35%?
If you did ln 35, then you would have to do ln of 100.
Okay.
Right, so I gave you an original concentration and told you 35%.
Oh.
Yeah. But what matters is it's 35. So it doesn't matter what values you plug into 0 and t, as long as they are 35% of each other. Yep. Right, we don't know t, so that we're looking for t, and then we have ln of, I said 0.1. Right, you could plug in 1 and 0.35, you can plug in 100 and 35, you can plug in 0.1 and 0.035. It's just magnitude difference. So then you can solve for t. So I got t is equal to 9.63 days. Right, so I always like to look at T1/2 and say, like, or the t for time that takes, and ask myself, does that make sense? And if I look at a half-life, right, this is going to be T1/2 and this is going to be T1/2. So in that first initial T1 half from 100 to 50%, that is 6.36 days. I myself am at 35%. So I am somewhere in between a full second half-life and my first half-life. So if it were to take 2 half-lives, it would be 12.69, right? Or 12.72. 12.72. But I'm at 9.63, right? I am 9.63. I'm in between a first 1 half-life and 2 half-lives. So that makes sense to me because I'm at 35%. I didn't fully make it all the way to 25, but I'm not at 6.36 because I'm not at 50%. Okay. So I like to always just check in there. That doesn't finish our question though. We're asked for it in minutes. So we have to take 9.63 days. Right, there's 1 day is 24 hours. 1 hour is 60 minutes. And then you can do the math from there.
So it would be the same premise for like the zero order second, just using that.
Yep.
equation.
Yep. If it's at 0, then you just need your 0 with stuff. And if it's at second, you just use your second stuff.
Can I ask you a question about equilibrium expression? Alright, so this is, it has an equation, it just wants you to write the expression for it. Can I say? So on the reactant side, you have two PB3 and O4. And on the product side, you have 6 PBO plus O2. And the only gas you have is your oxygen, your O2. The rest are solid.
Okay.
How would you write that out?
Yep. So in your equilibrium expression, you can only have aqueous or gaseous.
It wants this as gas.
Yep. You can only have aqueous and you can only have gaseous stuff. So if everything's a solid, then your only thing you're going to put into your equilibrium is the gaseous compound.
That makes a lot of sense. Okay, because this is a homework question I got put on.
Yep.
I see.
Yep. Yeah. No liquids, no solids. So it'll just be aqueous or gaseous.
Okay.
Yep.
Wait, sorry, what was the examples for the solids and liquids?
Yep. So for K, like this guy up here, you can only put gases and aqueous compounds in it. No solids, no liquids.
That's just for K, but
That's just for big K, equilibrium. All right, any other questions? I'll be in class on Friday, so you can find me before class.
I have a question about homework. I think I have to share it to you.
Okay, great. So we can wrap it up for today and we'll call it good.
Is your last in person?
This is my last in person. It will be